thanks for joining today. We're really happy to have, two of our strategic vendors, both Wolfspeed and Analog Devices, together on this training session. Joining us, we've had a great relationship with both, and seeing these two working so closely together tremendously benefits us. In fact, last week, Wolfspeed and ADI and a third thermal vendor were on a panel discussion with PCIM days, digital days, and had a great response. So they got a lot of good material to go over. So it's from Wolfspeed, we have Power Platforms Manager Adam Anders, and from Analog Devices, Senior Systems Application Engineer Eric Benedict. And again, team, if you could mute your phones, mute your computers, picking up some background there. I appreciate it. So without any further delay, I guess, Adam, I'll turn it over to you.
All right, thank you. So good morning, good afternoon, or good evening. I'm Adam Anders with our Power Platforms team at Wolfspeed, joined with Eric today.
Yep, and I'm Eric Benedict with Analog Devices, as application engineer, working on our gate drives and working closely with Adam and the folks at Wolfspeed.
Right, so today we're going to talk with you about some of the most important and frequently asked topics when it comes to designing with silicon carbide. The faster switching speeds of silicon carbide MOSFETs compared to silicon FETs and IGBTs is one of the main benefits of using them, because it enables more efficient and power dense designs. However, these higher speeds impacts other aspects of the design, and those aspects become much more critical, including gate drive, short circuit protection, and circuit parasitics. So today we're going to take a look at these topics and provide you with the information that you need to help unlock the power of silicon carbide in your designs. So we'll start by going over the Wolfspeed and ADI partnership, talk about gate driver considerations, go into short circuit protection and the effects of PCB layout on performance, and finally finish up with looking at what the effects of that high DVDT switching has on the circuit. So just some background information on our companies. I'm sure you're very familiar with them. Wolfspeed's the global leader in wide bandgap semiconductors, and our silicon carbide power MOSFET portfolio offers some of the best performance on the market today. And silicon carbide is being adopted across every industry now at a very rapid pace, especially in automotive as a growing target market. Analog Devices is the market leader in digital isolation with the #1 market share and over 3 billion channels of digital isolation shipped. ADI's gate drivers offer some of the highest CMTI on the market, and they therefore are designed to work very well with our silicon carbide MOSFETs and complement it very well. So we've teamed up our two companies as respective industry leaders to come up with really great solutions to support silicon carbide environment here and help our mutual customers in designing it into their own systems.
Okay, so as Adam mentioned, we're working together to, help our customers design good solutions. So we have a growing number of evaluation platforms and reference designs that allow our customers easy evaluation of Wolfspeed's silicon carbide switches and Analog Devices gate drivers. It provides a good starting point for a successful product design. We have companion gate driver boards for the BM2, XM3, and Wolfpack modules, and a couple different inverter reference designs for the XM3 module. For evaluating discrete switches, there are also test platforms in addition to reference designs. And of course, full design documentation is available for all the designs on both companies' websites. Here we go. And so just kind of give a list here. We'll flash. Oh, too fast. There we go. Here's a list of all the things that are available with kind of showing the part numbers that are involved, so you get that detail Again, things are on Wolfspeed and analog.com. And then we've developed this companion guide that basically makes it easier to kind of match up which gate drivers and which switches for which applications tend to make sense. So down at the bottom in the right, there's a decoder ring for the letter codes in the table. But basically the way this would probably work easiest for usage is you start here kind of looking at the switch in terms of the switch needed for your application, and then you can move over and you see the different types of gate drives and what can work for your application. The gate drives are organized here with the performance class, which basically just provide good, strong gate driver basic functions. Then we have the protecting class that adds overcurrent protection, other fault protection detections, and then the programmable gate drivers that add full programmable configurability. So this shows kind of the depth and breadth of both Wolfspeed's portfolio and Analog's portfolio. Okay, so if we jump into some of the gate driver considerations, one of the things I want to talk about is, is the peak current capability. So why is that an important feature in driving the switches? So in most cases, it's going to come down to efficiency in the form of reduced switching losses. In order to complete the switching transition, the gate needs to deliver enough charge to the gate so that the switch is fully on. Speeding up the switching means delivering this charge faster, and since current is charge versus time, faster switching means more gate drive current. Is a reasonable simplification outside of the Miller plateau. We can model the switch's gate source as a capacitor, and so the gate circuit is effectively an RC circuit. Thus, the peak drive current is going to be determined by the gate supply voltage and the total resistance in the gate loop. While the external gate resistor is clearly present here, the driver's internal RDS on and any internal gate resistance in the switch also needs to be accounted for. One thing I want to mention is when you're looking at different gate driver data sheets is that there are going to be different test conditions that how the manufacturers report their gate driver output currents. Some specify currents that are achieved during a very short circuit pulse where you short the output, while others use currents that are measured when you have some realistic gate resistance that are present. So you do need to be careful when comparing specs from the different devices.
Okay, so we'll look at the two generations of Wolfspeed MOSFETs that are on the market today. We have our second generation and third generation parts. So the second generation parts use a 20 volt gate drive voltage for their turn on level and -5 for the turn off level. We've since migrated to a +15 volt on our third generation parts and a -3 to -4 volt for turn off on our third generation. And that's going to continue into the foreseeable future, into our any future generations we plan on coming out. We'll stick with that third generation drive levels to enhance compatibility going forward. So when you look at designing a gate power supply, the first thing you need to know is how much power do you actually need from that supply. So to calculate that comes into several different factors of the circuit. So it's the switching frequency, the gate charge of the device, any additional capacitance placed at the gate of the device. We often will have a 1 nanofarad capacitor attached to the gate of our devices to help increase immunity to turn on transients and reduce some ringing. It also, the total power depends on the voltage swing, that turn on to turn off voltage swing. So 18 to 19 volts in our case for the third generation parts. And then if you're paralleling any parts, obviously those need to be accounted for. And then just other ancillary loads, the gate driver IC needs power, the gate source resistor, 5 or 10K hanging across the gate to keep the device off requires a little bit of power. And then if there's any other circuits or indicator LEDs, things like that, would also need to be accounted for when designing a gate power supply. So I'm not going to walk through the whole formula here, but it's pretty, the key takeaways are that it's proportional to the gate charge and the switch frequency. Those are kind of the two big variables that a designer is playing with when they're selecting different parts or designing a application. So just to take a look at where some typical applications would fall, the chart on the left here shows kind of 3 typical applications. So in the corner, there's the PFC or power factor correction. Typically, those are lower power, a lot of industrial and server power supplies, single phase PFCs, or UPS and other things like that that'll have a PFC front end. Those end up typically having a fairly low gate power requirement, just because they're often in the 50 to 100 kilohertz frequency range on switching frequency, and they're at that lower power level, so the devices have smaller gate charge. Therefore, they have typically a low power. Not to say that you can operate beyond these, but these are kind of standard areas. You'll see we call out 4 different specific points here. These are actually some of the ADI Wolfspeed reference designs, just as a frame of reference where some of our projects have fallen in these areas. So above that is the 3-phase inverters. Again, those are typically lower switching frequency, anywhere between 10 and 40, 50 kilohertz typically, maybe up to 100 in some cases. The reason that those are often higher in power is that those are usually large modules in those applications, and so they have a higher gate charge that needs to be fed. Then over here we have resonant converters, so LLCs, CLLCs, things of that sort. Those operate at very high switching frequencies, and so that's what's driving the gate power up in those regimes. But they're typically discrete devices, and so they don't have a very high gate charge. So you can kind of see these 3 main trends, but it gives you a good feel for the general power requirement, anywhere between below a half a watt for PFC up to there's really no limit on 3-phase inverters. If you get up into the megawatt level inverters, that gate power can get very high overall with parallel devices. The plot on the right here just shows specific parts. So our XM3 module is the purple line here. You can see that has a very steep curve because it has very high gate charge. And so just a small increase in switching frequency increases the power requirement substantially. The blue curve is one of our largest discrete devices. So it's a 16 milliohm 1200 volt part, and that's got a pretty hefty gate charge because it's a large die in there. And so that one still increases fairly quickly as well for a discrete part. If you drop down to this gray line here, that's a more manageable size 60 milliohm part. So it's a smaller die than the 16 milliohm, and therefore you can see that it can easily go out to very high frequencies without the gate power going up substantially. And then just as a reference, there's that 1 nanofarad cap that I said we often recommend putting on the gate to get a feel for how much power that requires. So the overall trends from these, basically the higher the system power, you're typically going to have higher gate power requirements because that requires larger die or parallel die to achieve those levels. Therefore, your gate power is going to be higher. Likewise, with the switching frequency, gate power is proportional to switching frequency. So anytime you increase that, you're going to increase gate power.
Okay. So, as Adam's talked about, depending on the device and the switching frequency, you've got, somewhere between a half a watt and up to several watts of power. Because the MOSFET gate basically is a capacitor, all of the power that we're talking about here is going to be dissipated in the lossy components. So those are basically the gate driver's output stage resistance, the external gate resistor, and the MOSFET's internal gate resistance. So being able to calculate what the power dissipation is on the gate driver to make sure that your selected gate driver is going to be able to handle the application, you need to basically use the ratio of the internal resistance to the external resistance, so that you want to basically have most of the power being dissipated externally from the gate driver. So again, having a low RDS on for both the turn on, the pull up FET, the P FET, or the turn off end FET, you have to calculate both when you're doing that. Okay. All right, so now, we looked at where the power is going to go. How are you going to get it? And there's a whole bunch of different solutions that are available, mostly because there isn't any one particular right solution. It's going to depend on the application. So metrics you can look at when comparing the different power supply solutions include, the size, the layout, how complicated it is, the cost, performance, flexibility, and with some of the newer applications, automotive with electric vehicles, you start looking into safety redundancy as well. So for some of these simpler designs where low cost is going to be very, very important, and you have a low voltage, low power need type of thing, the bootstrap works really well. So there you're basically using the switching action of the converter to basically charge a cap that provides enough power to keep your gate up and running. For small devices where you are going to have, a varying, continuous duty cycle switching, things like that work. But if you want to have it always on, something like this isn't going to work. Another solution that is common is the flyback or a multi-tap type configuration. So there you're going to add some extra components. You build a little flyback. It could be the flyback controllers inside the gate driver. It could be it's a totally separate thing. You're going to have more parts, more cost. But if you have a flyback for each gate driver, now you have good efficiency and regulation, and you can get the voltages that you want. The multi-tap often is the same flyback type thing. So you have a single transformer with a single driver. But now things get large. The transformer, instead of being small, gets to be quite large. And you've got, you can do different voltages, but now you can't regulate as much. You only can regulate for one of the supplies. So you get some trade-offs there. A common solution, especially from ease of design, is to use an isolated DC to DC converter brick. Okay, so now you get exactly the voltage. Some of them can have okay efficiency. They may be a linear regulator inside, but you get good regulation. Could have a small footprint, but the cost, buying that integrated solution is going to be expensive. Often, also, sometimes if you look the size, here's the DC to DC converter footprint wise. Here's your gate driver. The supply is bigger, and if you look at it on profile, like the multi-tap transformer, this power supply module there is going to look like a skyscraper compared to the other parts. So you have a whole bunch of different trade-offs. Depending on your application, there's one that's probably right for yours. Okay, so dig into a little bit now on the short circuit protection. Okay. So Before we get into short circuit protection, I briefly want to touch on the differences on the output characteristics between MOSFETs and IGBTs. A lot of folks are familiar with overcurrent protection in an IGBT, and the difference between the way the two devices work internally has great impact on how the protection, how that performs. So IGBTs have a defined active region, okay, where they have a nice defined current limiting characteristic that's easily distinguished from their saturation region. So it's easy to determine when the switch leaves the saturation region because the drain source voltage, or actually not drain source, the collector emitter voltage is going to greatly increase. So this, from a short circuit protection, we call this region the desaturation region that you can easily detect. The active region's current limiting characteristic also is going to help with limiting fault current prior to the protection circuit detecting, because you're going to clamp at some fault level. Conducting MOSFETs, however, are either in the ohmic triode region or they're in a saturation region. The transition between these is going to be much less pronounced, as you can see comparing the two curves. And so while similar protection circuits are used, you do need to adjust your performance expectations in terms of what is realistically achievable with a silicon carbide device. So with a IGBT, it's going to be feasible to have a desaturation detection circuit that can detect and react to overload conditions as well as larger fault conditions. For silicon carbide MOSFETs, we believe the expectation should be focusing on protecting against the larger fault conditions using the gate driver protection, and then use the control system with the fast control loop to detect and handle overload conditions. All right, so here is an example. Kind of, we'll start off with the bad news of what we want to prevent. But here's an example of a destructive test on a silicon carbide module showing the waveforms and timing of a short circuit event. So basically, we're turning on a switch into a fault, and you can see that the current is ramping up very, very quickly. And it takes about a microsecond for it to enter saturation, where then the current starts to be limited. And then, after about 2 microseconds, this particular device is damaged and things go on. So if we want to be able to detect and protect the device, we're going to have to do it not when it reaches saturation, but while it's still looking at a transient. So the silicon carbide protection is really not so much looking at a particular current, but looking at a rate of change, kind of how fast is that current going. So you're looking at a change in the fault impedance, if you will. Okay. So if we look at the circuits that are available for short circuit fault detection, there's basically two methods that are available out there. There's the fault detection method that looks very similar to a IGBT style desaturation detection circuit, and then there's a current shunt sensing method, or indirect drain current sense. So the desaturation style short circuit protection, again, has a blanking switch to prevent false positives when the switch is off or is in the process of turning on. Once the switch is released, the sense node, basically right here, increases in voltage by charging the capacitor C1 through R2 and or a current source that's present inside the gate driver. And this basically continues until this voltage is large enough to forward bias these diodes above the drain source voltage of the switch. And so then this basically rides just above the drain source voltage. And if the drain source voltage starts to increase because of a impedance change or a fault, then you can detect that and turn off. You can adjust the trigger voltage, effectively. There's a fixed voltage that's in the gate driver. It may be adjustable depending on the gate driver, but by adjusting your component values here, R1, D1, D2, and or additional diode in here, you can then adjust where that effective trigger point is. Or if you need to adjust it in the opposite direction in a downward way, so that you have more voltage, a higher voltage on the drain, you can use a voltage divider across here. So by choosing your components, you can effectively adjust the trigger point for whatever your application needs. So this has the advantage of basically having fairly low power dissipation, because you're not putting any sense components in the current path, and you can adjust it to tune what you need to have for your application's short circuit trip. The shunt-based method is measuring the current through the shunt resistor, and then when it increases past a threshold, you can trip. So it works well if you have lower power converters, because you're basically going to be putting all your load current through the shunt resistor. For small converters, the shunt resistance, the power dissipation for that won't be too bad, and it works fine. For larger power converters, the power dissipation for the shunt resistor is going to be a limiting factor and is not usually practical for the larger applications. Okay, so one of the things that's important after detecting the fault is how you're turning off the fault. So kind of like Goldilocks, you need to turn it off fast enough that you're protecting, but not so fast that you're damaging the device. Because when you turn off the switch under a fault condition, you're going to have a much larger fault current, and you're going to have a lower impedance that's present. And so if you're turning off very quickly, you're going to have a high DIDT because you got more current and you're trying to turn off quickly. So both of those make that grow, and then whatever the parasitic inductance you have in the circuit is going to add a voltage that's going to add on to the drain source voltage and can potentially damage the switch. So if you don't have the turn-off circuitry for the fault just right, you may detect the overcurrent condition, start to turn it off, and then still damage the switch, not because of overcurrent, but because you've turned off too fast and you've overvoltaged the switch. So it's important that when you're choosing the turn off, it's going to be a little slower than the normal turn off, because you have a higher current, so you don't want to turn off as fast, but you also don't want to turn off too slow, because then you're going to spend too much time in that power. So having the ability to externally adjust your turn off is very important, especially for the larger silicon carbide devices. Okay. All right. So in terms of looking at what happens with the protection, where things are successful, here's an example of what can be done. So here, what we're doing is introducing a hard switch fault, which is one of the harder cases to protect against. We basically provided a short circuit between the DC bus and the midpoint, and then we're going to turn on the switch into that short circuit. Okay, so there's going to be very, very little impedance that's present to limit the fault current, so things can get out of control very quickly if we're not protecting carefully. Okay, so what we're displaying here is the drain source voltage, the short circuit protection sensing node, the VDC DE SAT node on the gate driver and the gate voltage to see what's happening. Okay, so basically what we have done is we've got the turnoff in this case that limits the overshoot voltage to just about 300 volts. So we have a total stress of 1.1 volt or 1.1 kilovolts. So this is a 1200 volt device, and basically you can see the timing waveforms that are happening. So the blanking switch that's holding the sensing node off is happening in this region, which is about 300 nanoseconds. And then we have the ramp time where the sense node is charging up. And then there's the delay for the comparator to react and turn off. And then this is where we do the soft shutdown. Okay, so basically we're detecting the fault here in about 550 nanoseconds. And we get about 360 nanoseconds for the turn off, and that protects the device. You can see that we're doing this completely within less than 1 microsecond. And so this is, going to be able to protect and provide good protection for the device. If we go to the next slide, you can see the same event, but now instead of the DSAT node, we're plotting the drain current that's coming through here. So we're keeping the current, this is a 450 amp rated device. We're keeping the transient peak current, under 1 to 1.8 amps or kiloamps. And so it's, around four times the rated current. When you look at the energy that is being dissipated here for this fault event, it's 136 millijoules, which is about 10 times what we would have in the normal switching event. So it's basically providing very good protection, limits the energy, and the device will be just fine coming through from that.
All right, so let's take a look at the effects of the PCB layout on switching performance and behavior here. So this shows a typical boost converter setup just as an example here to illustrate all the different parasitics in the circuit. So what you want to be aware of is, as we mentioned, silicon carbide is much, much faster than silicon technologies, MOSFETs and IGBTs. And as a result, these parasitics become much more critical in these designs. You want to avoid taking a design that was done for silicon and just dropping in a silicon carbide part because it fits in the same holes and call it good. You'll probably still see an improvement with the silicon carbide part in that situation just because the technology is superior. But to really get the benefit out of it, the layout needs to be optimized. So when we look at the parasitics that are important here, there's a few different loops to consider. So if this is our MOSFET, there's parasitic inductance in all the traces. There's parasitic capacitance across the device. And these things all come into play here. So inductance is in series with your MOSFET and the bus capacitors is going to increase the overshoot at turnoff, just like Eric was talking about. Under short circuit conditions, it's amplified, but even under normal conditions, any DIDT in these inductances is going to increase the voltage that the part sees relative to what the bus voltage actually is. So minimizing these inductances allows you to drive the MOSFET harder, which is going to reduce the switching losses in it. If you have a lot of stray inductance in here, you have to increase RG to slow down the device so that it doesn't overshoot on voltage. And then you give up a lot of the switching benefits that you could realize. Similarly, capacitance across the device. Anytime you turn the device on, that capacitor's energy is going to discharge into the device. So you definitely want to avoid adding stray capacitance at any of the switching nodes, because that's just going to end up translating directly into losses in the device. This other loop 2 here represents the gate driver loop. So any impedance between the gate driver and the actual gate of the MOSFET is going to act to slow down the switching. And it can even, it's going to reduce the control that you have over the gate voltage at the actual MOSFET. So anytime there's inductance and capacitance in a circuit, there's a potential for ringing and overshoot. And so even though your driver is driving -4 to +15 volts, the voltage that the MOSFET sees could be higher than that transiently, which could lead to damage of the gate oxide. So you need to keep this loop physically short on the circuit board, and also use techniques like a Kelvin source connection for the gate driver and a copper pore source between the gate driver and the MOSFET to reduce the inductance in the gate drive loop. Loop 1 here on the input side, this is particular to a boost converter topology. These inductances don't matter so much here since you have a intentional inductance. So the actual inductance isn't critical. But what this represents is, any non-ideal flow in this power path, those inductances can actually end up radiating noise out into the system, and those will give you a hard time when it comes to meeting EMI and EMC compliance tests, because those can turn into radiators there. So the next aspect to look at is actually the package of the MOSFET itself, and this is very critical here. So TO247 packages, everyone's familiar with them. They've been around forever, and they're great as long as you're not trying to switch fast. With silicon carbide, these leads are inductors, right? Reaching up from the board to the actual die in the package. And so that inductance plays into the circuit diagram that I just showed, and it's actually part of the device. So newer packaging like the 4-pin TO247 is a great alternative here. It adds a Kelvin source connection. And what that does is illustrated here. The inductance in the power path on the source pin in the traditional TO247 acts to actually reduce your gate drive voltage at the moment of turn on. Because as you're applying a gate voltage here, current is increasing through the device. So you get this voltage drop across the source pin. That's actually going to act to subtract off your gate from your gate drive voltage, since your gate drive is connected outside of that inductance. And so that's going to slow down the turn on event and therefore increase losses. What the Kelvin source pin does is it makes your gate drive connection above that source impedance in the power path. And so this inductance then doesn't have an impact on your gate drive voltage. So your gate driver is able to charge up the gate capacitor in a more controlled and faster fashion. You can see that in the scope traces on the right here. The current is in red, and so the faster rising one is the Kelvin source part, because it's able to turn on faster than the traditional 3-pin part. Similarly, the voltage in blue here drops a lot faster with the Kelvin source part. And so when you look at switching losses, it's the current times the voltage and the integral under that curve. So the faster these transitions occur, the less switching loss you're going to see. So just to drive that point home here, if we compare 3 different packages under the same set of conditions, same gate driver, same board parasitics and things like that. If you look at the high current point here with the 3-pin device, and then drop down to the 4-pin with the Kelvin source connection, there's a dramatic decrease in switching loss. And it's less than half of the switching loss of the 3-pin device because of that Kelvin source connection. A further improvement can be made if you even go down to a part that has shorter leads in general, like the D² package that we offer. it also has Kelvin source pins for the gate drive, but even the power drain and source connections are lower. And so you can see the overall inductance of a TO247 lead ends up being about 12 nanohenries, and that's the same in either case here. The 4-pin one improves performance because that inductance isn't, for the gate drive, isn't sharing the same pin with the power path. And so that's why you see an improvement here. But you get an even larger improvement in the surface mount version because the total inductance drops down to just 2 nanohenries because of the shorter leads and shorter connection to the circuit board. So anytime you have the flexibility in a design to go to a Kelvin package, it's definitely worth it to see the performance improvements and just overall better control of the gate with those packages. One other aspect we touched on a little bit was the stray capacitance in a circuit board layout. So you can see basically every node in a circuit board has capacitance to every other node to some extent. But what we highlighted here was some of the critical ones and the ones that end up contributing significantly to the performance. So like I mentioned, the capacitor across the device is very detrimental to performance because every time the device turns on, that stored energy gets dumped right into the device. That's direct heating of the device at the switching frequency. Some of these other capacitances, especially in resonant topologies, can affect the soft switching capabilities and the timing of those events and the dead times. And so it's somewhat topology dependent for these other ones, but you definitely want to make sure as you're doing a layout that you understand the implication of any stray capacitance in the layout and how to optimize that. So from a, and just for reference here, so if you have 1 square centimeter of overlap on a trace, so like say your top layer is connected to one node and your next layer is connected to a different node, for every square centimeter that those overlap, you're going to see about 38 picofarads of capacitance. While that might not seem like much, with a 400 volt bus between those nodes at 100 kilohertz, that's 0.3 watts. And so 1 square centimeter is also not a very big area. So when you consider designing a power board that has big heavy traces for carrying the current, you can end up with areas many times this. And so you need to make sure that they're not overlapping and coupling to planes that they shouldn't be coupling to, both from a noise perspective and from a power loss perspective, because that's just extra loss in your circuit that you need to handle. So we have an example of a real design here with version 1 and then version 2 where we paid closer attention to these capacitances. And you can see, same design, you're able to minimize those capacitances if you know what you're looking for. The first time around, maybe we didn't pay attention to the capacitances and didn't realize the impact, but you can see here how big of an impact that has on the system performance. So just by focusing on reducing the capacitance of those 6 nodes, it made a significant difference in the efficiency and a 25 watt improvement in power loss just from changing the layout. So definitely things to keep in mind, that all these PCB layout things that may not have been critical at 10 kilohertz with an IGBT are super critical at 100 kilohertz with silicon carbide. So just to summarize some of these best practices for PC boards, anytime it's possible, you want to use a Kelvin source connection part. Use a source pore between the gate driver and the MOSFET to minimize the inductance in the gate drive loop. Use the shortest leads possible. So I mentioned each of these leads is 12 nanohenries. That's at the longer length. If you can drop that part right down onto the board, that loop gets much smaller and the inductance gets smaller and you're going to see performance improvements. The Distances are critical in general, so distance from the MOSFET to the bus cap, distance from the gate driver to the MOSFET. Those distances are all correlated to inductance. So the tighter everything can be, the lower all those parasitic inductances will end up. And then as far as the DC bus is concerned, inductance is determined by the loop area. So having overlapping pores between the plus and minus bus is going to reduce the loop area to just the thin layer between the circuit board layers and really help minimize the bus inductance. Similarly on this was kind of focused on discrete devices, but similarly on a module, having laminated bus structure will accomplish the same thing at that power level. Then in terms of capacitance and capacitive coupling, minimizing the overlap between switching nodes and any of the other signals or buses. Didn't talk about this one, but keeping sensitive signals away from high frequency magnetics with the high switching edge rates on silicon carbide MOSFETs, there's going to be some radiated noise around the magnetics, and that can couple into circuits and cause undesirable noise. So you want to be aware of where you're locating signals relative to the magnetics. And then keeping separation between the power loop and the gate driver loop. You don't want to be running high power traces underneath the gate driver, again, because it can pick up interference and cause undesired operation. So try to separate a power side of the board and a control side of the board. And then we didn't focus on paralleling in this presentation, but the high level takeaway there at paralleling is symmetry, keeping parallel devices.
Bien. C'était ta journée?
Sorry, I think we've got
Crevant,
some background noise.
Yeah, please mute your phones, guys. Yep, go ahead.
All right, thanks. So keeping symmetry on the parallel devices is probably the most critical thing there, and using separate gate resistors.
Okay, so kind of wrap things up here. Want to talk about some more of the considerations that, now we've got the switches switching very quickly. You're going to end up with some high DVDT issues that need to be looked at. Okay, one of them is the common mode transient immunity. Often folks think of this as kind of a disturbance rejection or rejecting noise, but in reality the common mode transients are inherently generated by the switching action of the power converter. So when we're doing the normal switching action, we're going to basically move this node up and down. And as Adam was talking about with the layout, you want to minimize your capacitance here so that you're not charging and discharging the capacitance as much as or any more than you need to. But there is going to be capacitance in the isolated gate drive and power supply that are going to be present. And you want to minimize those, but you're still going to have them happen. And the switching action is going to charge and discharge this capacitor. So you're going to have a common mode current that flows through the gate drive, throws through the power supply, anything that's between the switching node and ground. Okay. And so focusing on the gate driver, because that can cause problems in the operation. You're having this common mode current that flows through the gate drive isolator, and that can cause problems with the isolator, especially if it's a capacitive isolator. Then you got capacitance in the barrier. It looks like a capacitor. The current's going to flow right through it. So if the isolator in the gate driver isn't properly designed to be able to handle those large currents, you're going to have issues. You can have timing jitter, transmission errors where the gate drive doesn't go when it's supposed to. Conceivably, you could even have isolator damage, though with pretty much most modern gate drives at this point, they don't get damaged, but they'll have problems with the signaling. Common mode transient immunity is the level of the transient you can apply that doesn't have an error. Now, again, you need to look at what the data sheet is saying when they say what the no error is. Many gate drivers are specified for their CMTI at a static. So if the gate drive is on or the gate drive is off, there's no disturbance in the switching operation, which is good. However, if you're wanting to really push your efficiency, push the switching speeds, you want to be able to tighten up your dead time, which then increases your efficiency. And in those cases, you really need to have good, solid timing. And when you start looking at the impacts that CMTI has, for a static error, you get a transient in that, you get a voltage transient across the isolator, that can cause it to toggle when it shouldn't. Okay. But then you start kind of looking at more subtle levels of the impact. You get into a dynamic error where you have the common mode transient, and then this is the input signal, the output signal, and sometimes depending on when the transient is happening, you might cause it to have an issue and the transition happens, but it doesn't happen within the timing specifications. You can also have timing jitter, where you have the transient, the output signal disturbance is still within the specifications for the data sheet, but you have this variation. And so you have to accommodate that when you're looking at the dead time. And then, again, coming in, ideally what you want to have is no impact. So you can have common mode transient that's applied, and it doesn't matter when it's applied, there's no impact on the part. Okay. So one of the things, these two cases here, the part doesn't meet the common mode transient level, but in this case, it does. And so you can have parts that will still, quote, meet specifications, even though they may have very large jitter and disturbances, but they're still within the timing specs. So if you're going to be, really pushing your dead time, really pushing to get maximum efficiency, you want to have a part that has very, very good common mode transient capability type of thing.
Okay, and then just final note on isolation capacitance in general. So as Eric mentioned, that's inherent in any component that crosses the isolation boundary. So the gate driver, isolated power supply, any isolated feedback circuits, they all are going to have some inherent capacitance there. And since the MOSFETs produce high DVDT, there's going to be some parasitic current flow from the high voltage side to the low voltage side. So I guess the message to take away here is when selecting parts and doing layouts that you want to make sure to minimize the capacitance there. For instance, 2 picofarads of capacitance with 100 volt per nanosecond DVDT on the MOSFET can give 0.2 amp current spikes across that boundary there. They're very short-lived, but they can cause noise issues on your low voltage circuitry, analog feedback, things like that. So overall, trying to just minimize that capacitance is going to give you a lower noise system at the end of the day, help with EMI performance as well. So just to wrap things up here, I think we covered a lot of different topics here and can certainly dive into topics more deeply on a smaller basis. But just want to highlight that silicon carbide enables really high efficiency in systems, high power density, but it does come with some of these design challenges that we touched on because it switches so fast. And so it's important to select a gate driver that has sufficient drive capability to take advantage of those switching frequencies and bring the losses down. But it also has to have proper immunity to be immune to those common mode transients. And then, focusing on the layout, really dialing in a design to be tuned for silicon carbide, minimizing parasitics and things like that will really help highlight the benefit of the high switching speeds. And then another point to focus on is the DSAT or short circuit detection is different slightly than a IGBT. And if that's an important aspect in a design, especially on the module level or the price of the module, makes it really make a lot of sense to have short circuit protection to avoid a catastrophic failure. Trying to keep that detection and shutdown time as short as possible, under a microsecond is a safe target. Those are kind of the key design aspects, and just want to let everyone know that Wolfspeed and ADI are here and working together to help support our evaluation boards, reference designs, and any customer questions or support issues that we can handle there.